how it works, look at this video from ITT Automotive, a company that manufactures ABS systems. First, watch what can
So the next question is,
happen without ABS.
while it's skidding, it experiences friction, right?
Then, with
While it's not skidding, it still experiences friction.
ABS.
All right, so the question is, why is it that it's experiencing more friction while it's not skidding than while it's skidding? So that's what the question is. What's going on there? Okay. All right, so she's pushing up against the file cabinet, right? What's the net force acting on? Oh, forget that. What's wrong with this picture? Let's discuss that briefly. If somebody is pushing up against the file cabinet in this fashion, what do you think is going to happen to the file cabinet?
It's going to tip over.
It's going to tip over. Give yourself 5 points, guys. It's going to tip over. This, whatever the artist says, this is not from one of my art students. Whatever the artist says, I got it wrong. You can't just push like that. That's crazy. It's going to tip over if you did it.
No. Yeah. I gotta go.
Tom, could you call me an ambulance? Hey, hang on. I was waiting for that.
Need another phone line?
All right, so it's going to tip over. So just ignore the fact that it's going to tip over. All right. Will this file cabinet move under the circumstances? Let's analyze what's going on. So there's going to be a push here. It's got some weight, right? On top of that, the surface is going to offer some traction. So there's a frictional force acting on it, correct? All right, so what's the net force acting on it under the circumstances? Look at the forward force, size of the forward force. Look at the size of the backward force. Which one is larger? They are the same, right? This force is going to be the same as this force. All right, so the forward force, backward force, they're in opposite directions. They got the same magnitude. So if that's the case, what's the net force acting on this one? Net force acting on it is going to be 0. Yeah, it's not going to move. This cabinet, file cabinet is not going to move. Okay, so if this is the best that she could do, this job is not going to get done. All right, so under the circumstances. So what does she need? If she's working at an office, she's going to go get some help from someone, right? All right, so she goes out and finds a coworker. Now both of them are pushing. Is it moving? Yes or no? All right, so once again, look at the magnitude of the forward force and look at the magnitude of the backward force. Size of the forward force compared to the size of the backward force. Which one is larger?
Look the same.
It's still the same. It's still not moving. Okay, notice that there's a force acting on it. There's a push acting on it, and the frictional force is balancing it. So the frictional force equals to the pi force. So the net force is 0. There's friction. This is known as static frictional force. Static means that this thing's not moving. Right? So this is the amount of force that's generated, frictional force generated while the surfaces in contact are remaining at rest with respect to each other. All right, so this is the static frictional force. One thing that I want you to notice is while she's pushing, look at the size of this force and compare it to the size of the static frictional force. So what happened? When both of them are pushing it, this got significantly larger, right? So the push got larger, the static frictional force became larger. When the static frictional force becomes maximized, and that's what it means here, this is the maximum amount of static friction that the surfaces will be able to generate. When you maximize the static frictional force, it's going to turn kinetic, which means that one surface is going to slide over the other one. When the static frictional force is maximized, it's going to start to slide. So what happens? Take a look at the size of the forward force and take a look at the size of the forward force from here and look at the size of the forward force there. Okay, the push did not change. It's exactly the same amount of push, except what happened is the static frictional force is maximized. As soon as you maximize the static frictional force, it goes kinetic, which means that it starts to slide. So which means that the static frictional force becomes kinetic frictional force. Static frictional force, I want you guys to focus on here, becomes kinetic frictional force. So the case goes from static, stationary to a sliding motion. Okay, so the other thing that I want you to do is I'd like you to compare the size of the maximum static frictional force to the size of the kinetic frictional force. Which one is larger? Static frictional force when it's maximized or the kinetic frictional force? All right, which one is larger? All right, which one is larger in slow motion? Which one is larger?
I think they're the same.
Okay, all right, let me rephrase the question. Which arrow is larger, the bigger one or the smaller one? The bigger one or the smaller?
The bigger one.
Yeah, the bigger
Ah,
one.
you guys, it's just in the wording, man. Or else everyone is so confused because you guys have never seen an arrow before, pointing in the wrong direction. All right, so obviously this arrow is bigger than this one is, right? So what that means is this static frictional force when it's maximized is going to be larger than the sliding or kinetic friction. So static frictional force, when the surfaces in contact are not sliding with respect to each other, they are going to experience a larger static frictional force while they're at the verge of skidding or sliding than while they're sliding. That's what it means. Okay, so you got two surfaces, and just before it starts to skid or slide, it's going to experience the maximum amount of traction or frictional force, in essence. Okay, that's what it means. You kind of know that the maximum static frictional force is going to be always larger than the sliding or kinetic friction. All right, there are two reasons for it. It says friction provided by the texture of the surface is going to be larger, when the surfaces are at rest with respect to each other. That's just partially correct statement in reality. Okay, so before I come back and clean this up, okay, one thing that you need to know: coefficient of friction in the static case. So surfaces are at rest with respect to each other, and the coefficient of friction for a kinetic case when one surface is sliding over the other one or skating over the other one. Okay, once again, rubber and concrete. Let's focus on the dry surface. So that's what we're focusing on, the dry surface. Okay. So in the case of static, it's 1.2. As soon as it goes in a skid, the traction goes down. It becomes 0.85. All right, so it becomes 0.85. Oh my God, what's going on? All right, so which means that we are going to be able to make a few statements. So let's make a summary statement. Let's go with a surface friction. All right, so frictional force in essence. We will have two kinds. One is the static friction. The other one is going to be the kinetic friction. All right, so static, and we will have kinetic. Static means the surface is at rest. All right, so that means that the surfaces will be at rest. And kinetic means this is the sliding friction. Sliding or skidding friction. All right, so the frictional force in general is going to depend on the coefficient of friction and the apparent weight. All right, so both formulas are the same, except in the static case, the traction number is going to be different than the kinetic case. Okay, one simplistic argument, and I will make a simplistic argument at this point. We know that the static frictional force, when it's maximized, is going to be larger than the kinetic frictional force, because you know that both of them will have the same normal force. The only difference is this will be larger than that. All right, so because the mu sub s for the static case, the coefficient of friction is going to be larger than the coefficient of friction for the kinetic case. That's it. All right, so the example of this, this is going to be 1.2 for tire on asphalt, and this is going to be 0.85. Okay, so that's the example that we have. All right, so that's a simplistic statement. So let's go with the conclusion for now. Okay, not bad. All right, so that's correct. So the kinetic friction is going to be usually smaller than the maximum static frictional force. It's not usually, it's always. D is the best answer. Okay, let's have a quick discussion. This one is a sliding tire, so it's skidding. And this one is rotating. So this one is a rolling tire. All right, so coefficient of friction for the skidding tire is going to be 0.85. And the rotating tire is going to experience the coefficient of friction of 1.2. Okay, here's a question for you. Why is it that the rotating tire is experiencing static friction? How's that possible? I mean, this tire, if you lock up the tires, this one is going to skid. So this is a skidding tire. This is a rolling tire. How does a rolling tire experience a case of static friction? How does the tire, which is rotating or rolling, experience static friction? What do you guys think?
Because it's not a forward force, it's rotational, and so it's not being slid or skidded, it's still rotating.
All right, Jack, I'm going to give you 5 points. I'm looking for something a bit more well-defined. All right, so here's what I'm looking for in case there's a test question, and you know these are the sort of stuff you see on the test. Okay, this point of contact, just take a look at the point of contact in both cases, guys. You got a point of contact here, you got a point of contact there, right? Here, the point of contact is skidding. All right, so this is definitely a case of kinetic friction, right? Here, the point of contact is static. Point of contact is not skidding. So this definitely is experiencing static friction. Because of the fact that the tire keeps rotating, the point of contact is going to keep changing. But whatever the point of contact is always at rest with respect to the surface, which means that it's never skidding. So that's the reason why the rolling tire will always experience the case of static friction. So that's what it means.
Here's how ABS works.
All right, now the next question.
If you need to brake suddenly, an onboard computer pumps the brakes on each wheel at up to 18 times a second, faster than you ever could yourself. That stops the wheels from
So while the tires are rolling, they will experience static friction.
locking up,
But why then do we have to lock up the brakes 18 times per second? That's what the anti-lock brake system does.
allowing you to safely steer around a hazard. All you have to do is apply steady pressure to the brake. You ever could yourself. That stops the wheel brakes on each wheel. An onboard computer pumps the brakes on each wheel.
All right, so the brakes
up to 18 times a second,
Brakes get pumped 18 times per second.
faster
Depending upon the car, it could be between 16 to 24 times per second.
than you ever could yourself.
So in this case, 18 times per second.
That stops the wheels from locking up, allowing you to
Pumping the brakes, how does that help?
safely steer around a hazard.
All right, short answer is pump the brakes will maximize the average static frictional force.
All you have to do is apply steady pressure.
So the question is, what's the meaning of what I just said? The pump the brakes will increase the average static frictional force. You're trying to maximize the average static frictional force. How does that go? Take a look at this graph, which I'm going to redraw shortly. All right, so here's the frictional force axis. All right, so what's happening is when you lock up the brakes, the force acting on it is going to be the static frictional force. And then what happens when the static frictional force is maximized? When the static frictional force is maximized, it starts to skid. So which means that the static frictional force will turn kinetic. Notice that only this portion of the static frictional force, this portion of it is larger than the sliding friction or the kinetic friction. So what does the intelligent brake system do for you? It's going to lock up the brakes for you. And then as soon as it's maximized, just when it goes into a skid, it's going to release the brakes and it'll catch the brakes, maximize it, release it, catch it, maximize it, release it, catch it, maximize it. It does it 18 times per second. It goes up and down within this region. So as a result, what happens is the average static frictional force is going to be larger than the sliding or kinetic friction. Okay, so let's go back and make the same argument one more time. All right, let's go back and make the same argument one more time. All right, so I'm going to make this the time axis. I can't make this the time axis, but let's make this the friction axis. Okay, so you lock up your brakes. It's all static friction until this is maximized. So which means that this static frictional force is going to be maximized. As soon as it's maximized, what's going to happen is boom, boom, boom. It's going to go into a skid. All right, so which means that it turns into a kinetic frictional force. One thing that you need to notice is only this region of the static frictional force is larger than the kinetic frictional force. So what the intelligent brake system does is it's just going to grab the brakes here. It's going to maximize it, and then it's going to let it go. Maximize it, let it go. Maximize it, let it go. As a result, the average static frictional force, this is the average static frictional force, is going to be larger than the kinetic frictional force. All right, so the average static frictional force. So it tries to maximize the average static frictional force. So this is the static frictional force. This is the average one. Maximum static frictional force is going to be right here. This is the maximum static frictional force. So the average static frictional force is going to be below the maximum static frictional force. So you maximize the static frictional force. It goes in kinetic. You grab it. You let go of the brakes. You lock up the brakes. It's going to become maximized. You let go of the brakes. You catch the brakes. And then once again, you keep repeating it 18 times per second. So the entire brake system is going to lock up the brakes about 18 times per second in order to maximize the average static frictional force. That's what it is. Okay, guys.